Okay. Thank you very much for the opportunity to speak and for organizing this really fantastic conference. I'm learning a lot of things. Today I'm going to tell you about some work that was done with my really fantastic collaborators, Eric Doker, Thomas Dumitrescu, and Efrat Gershkovitz. And this is really going to be part one of a two-part story that's going to be continued by Thomas after the lunch break. Okay, so just to start with some general motivations, of course, gaining insight into the strong coupling dynamics of gauge theories, including properties such as confinement and chiral symmetry breaking, is a very interesting but generally difficult and challenging problem. And so today I'm going to take an approach which begins with supersymmetry. I want to ask, how much can we learn about confining gauge theories by deformation from or perturbation away from supersymmetric gauge theories? And so, of course, when I have supersymmetry, I often have I have more tools at my disposal, and I can often determine many exact properties of the strong coupling or low energy dynamics. And so here we want to ask how much of this can I import? How much of this technology can we import to the study of generally non-supersymmetric gauge theories when I can connect them in some way to a supersymmetric one? This story I want to tell you is going to be about connecting a supersymmetric gauge theory in 4 dimensions to a non-supersymmetric one. And I'm going to tell you about the new perspectives that we can learn for its strong coupling dynamics. And I also want to emphasize that in this sort of program, there's a really nice kind of positive feedback loop between the properties of the supersymmetric gauge theory and also this sort of supersymmetry breaking analysis. So in particular, many of the detailed properties of the supersymmetric gauge theory will crucially inform the supersymmetry breaking analysis and go in detailed ways into determining the IR phase of the non-supersymmetric theory. And on the flip side, this supersymmetry breaking analysis has in some cases motivated new results in purely supersymmetric gauge theory. And so I want to highlight, and I think in the next talk also, we will highlight some of the new results in supersymmetric theories that have been motivated by these sorts of considerations. Okay, so today I'm going to be discussing the class of theories that I'll call 4D adjoint QCD. These are also the class of theories that were the topic of Georg's talk yesterday. What I mean is the 4D gauge theory with some number of fermions that transform in the adjoint representation of the gauge group. I'm going to take my gauge group in this talk exclusively to be SUN for general n greater than or equal to 2. I'm going to use a notation where NF, number of adjoint fermions, is the number of Weyl fermions. So this is 1/2 the number of Dirac fermions. So there's a factor of 1/2 relative to what we were discussing yesterday. Just a warning. The number of Weyl fermions is, sorry, yeah, the 2 is in the wrong place. Thank you. That's a stupid typo. Thank you very much. This class of gauge theories depends on n, the basically rank of the gauge group, and also NF, adjoint Weyl fermions. And so we can think about what its phase structure is as a function of these parameters. And this was really nicely reviewed yesterday. Basically, it's interesting to ask this question in the regime of asymptotic freedom. So for NF less than 11/2 in this case. There's some, like we heard yesterday, some conjecture for perhaps a conformal window near the asymptotic freedom bound, and it's still unclear where the bottom of this conjectured conformal window is. It's very the status of these higher NF cases is less clear. However, the two lowest NF cases are relatively well understood. So NF equals to 0 is of course just pure Yang-Mills theory with SUN gauge group. And this theory, it depends on the theta angle, and it's expected to confine for all values of the theta angle. There's a whole nice story there. NF equals to 1 has enhanced supersymmetry. So in this case, the one Val fermion is the gaugino in the n equals to 1 vector multiplet. And so this case is just the pure n equals to 1 supersymmetric Yang-Mills theory, in this case with gauge group SUN. And in this theory, we know very well that there are n degenerate supersymmetric vacua. They're confining and they're gapped. And their properties follow from the fact that the gaugino bilinear condenses in n equals to 1 super Yang-Mills. So these like n vacua. And so dialing up NF from what we understand to what we don't understand, we'd like to, in this talk, make contact with the NF equals to 2 case, by which I mean the case of one Dirac fermion. And here the status is really less clear. So in the first part of this talk, I'm going to first tell you what we might expect for the IR phase of such a gauge theory, this NF equals to 2 adjoint QCD in 4 dimensions. And then I'm going to describe how we're going to probe this expectation using an RG flow between adjoint QCD at low energies and 40n equals to 2 super Yang-Mills at high energies. So this is what I'm going to describe now. Okay, so first let's start with what might one expect this gauge theory to do. And so the standard lore for chiral gauge theories applied to this case of NF equals to 2 adjoint QCD, the one Dirac fermion case, would posit that the fermion bilinear condenses, leading to the properties of chiral symmetry breaking and confinement. So in particular, one would, this sort of gaugino condensate would lead to the following proposed chiral symmetry breaking pattern. That is that the SU NF equals to 2 continuous chiral symmetry is broken by the condensate to its U1 Cartan subgroup. And that the two Nambu-Goldstone bosons from the symmetry breaking pattern parameterize a CP1 nonlinear sigma model. Furthermore, we know in this theory that there's a discrete Z4n chiral symmetry. This is the remnant after the ABJ anomaly of the UN axial symmetry. And this sort of VEV would break the Z4n to a Z4 subgroup. So there's a chiral symmetry breaking of both the continuous and the discrete symmetries in this proposal of a phase. And the symmetry breaking pattern leads to, in fact, n copies of the CP1 sigma model related by this residual Zn. Furthermore, in this proposed phase, the Zn one form symmetry associated to the center of the SUN gauge group, which is of course unbroken in the UV by the adjoint matter, is proposed to be unbroken in this phase, signaling the property of confinement. So some immediate comments are in order. So the first comment is that the Vafa-Witten theorem applies to NF equals to 2 adjoint QCD, and it implies in particular that this U1 Cartan of the SU2 chiral symmetry must be unbroken. So of course, this is true of this proposal of a phase, but this is an important constraint that this must be true of any phase of the true phase that is actually realized by adjoint QCD. Okay. The next comment is that this sort of proposed phase is continuously connected in a precise way to the vacua of n equals to 1 super Yang-Mills. So what I mean is that if I add a small mass for one of the fermions, remember the n equals 1 case has one less fermion, one less Weyl fermion than this case. even if I add an infinitesimal fermion mass, what this does is it makes all of the CP1 vacua exactly degenerate, and these become the precursors of exactly the n confining vacua of n equals to 1 super Yang mills. So the fact that these phases are continuously connected is just some consistency check that that this phase makes sense. I don't need to invoke some phase transition to understand how to get at the n equals to 1 vacua. One, yeah, just one. Yeah, to get it at the NF equals to 1 case, exactly. Furthermore, I'd like to comment that this sort of story that I and Thomas are going to tell you has some, so we're telling some story of n equals to 2, Susie breaking down to n equals to 0. It's going to have some nice parallels to the n equals to 2 origin of confinement in the n equals to 1 vacua. And this fact that these sorts of vacua, these CP1 vacua, are close in this sense to the n equals to 1 vacua, kind of provides the intuition behind some of these parallels. So maybe this will become more clear as we go along. And finally, I also just want to mention, so this is some proposed proposal for a phase, but of course, other more exotic phases have been explored that are consistent with symmetries and anomalies and so on, including by some members of the audience here. So this isn't the only possible consistent phase of the theory, but this is what you might say, like the most naive guess for what happens. Okay, so our strategy to see if we can make progress on this question is going to follow from the following observation, and that's that I can interpolate between my NF equals to 2 adjoint QCD at low energies and n equals to 2, just pure super Yang-Mills theory at high energies by adding this particular supersymmetry breaking term, which is a mass term for the vector multiplet scalar, the complex vector multiplet scalar in the n equals to 2 vector multiplet. And this is a particular mass term that's non-holomorphic in the vector multiplet scalar. And then the statement is for scales of the supersymmetry breaking much larger than the strong coupling scale of the n equals to 2 theory, I flow onto adjoint QCD. And so at the basic level, if I delete the scalars in the n equals to 2 theory, then I recover NF equals to 2 non-supersymmetric adjoint QCD. And so in this flow, my two adjoint Val fermions are precisely the gauginos in the n equals to 2 vector multiplet. And in particular, a really important comment is that this mass term that I'm adding, the supersymmetry breaking potential or operator, preserves all symmetries of both the upstairs supersymmetric theory and the downstairs non-supersymmetric theory, except for supersymmetry itself. It breaks supersymmetry, but it preserves all other symmetries. And so also like Tifft anomalies are automatically matched in this RG flow. So for example, I said that NF equals to 2 adjoint QCD has this SU2 chiral symmetry. This is of course just the SU2R symmetry of the upstairs n equals to 2 theory. Similarly for my discrete chiral symmetry is the U1 part of the R symmetry of the upstairs n equals to 2 theory. And so now we want to use this supersymmetric embedding to explore the dynamics of, we're going to focus on SUN adjoint QCD. And in particular, the punchline is that we're going to present evidence that adjoint QCD with NF equals to 2 indeed does confine and break chiral symmetry as described on the previous slide. So that's kind of the punchline, and we'll describe how we get there. Okay, so some important comments are in order. So first, let me explain the leverages we have that are really going to allow us to attack this problem in a controlled fashion. So first of all, this supersymmetry breaking operator that I add, this non-holomorphic mass term for the vector multiplet scalars, it lies in a protected multiplet of n equals to 2 supersymmetry. In particular, it's the bottom component, the bottom scalar component of the n equals to 2 stress tensor multiplet. And so this fact can be used to track it on the moduli space of the n equals to 2 theory. And in doing so, this operator is matched onto the Kähler potential of the n equals to 2 theory. So this is a globally defined function, the Kähler potential given in terms of the periods of the Seiberg-Witten solution, or the generalization of the Seiberg-Witten solution to this SUN n equals to 2 super Yang-Mills case. Okay, so so at least for small supersymmetry breaking, we can reliably track this operator, and so when our supersymmetry breaking scale is small, we'll be able to reliably analyze the supersymmetry breaking potential and on the moduli space of the n equals to 2 theory. And I really want to emphasize that in this analysis, even in this soft supersymmetry breaking analysis, this really requires the entire n equals to 2 low energy effective action. So of course, it crucially depends on the Kähler potential on the moduli space. It depends on the holomorphic couplings in the solution. It really depends intimately on this data as determined by the SUN generalization of the Seiberg-Witten solution. So these things, these quantities really play a crucial role. Now, for the supersymmetry breaking scale large, we of course flow to adjoint QCD, and this is ultimately the limit that we want to make contact with. And so it is of course in this limit that we lose the strict reliability of this soft supersymmetry breaking analysis. And so one of our other punchlines, or one of our punchlines, is that what we'll be able to do is use this supersymmetric embedding to motivate a compelling dual description of the IR dynamics of the theory, and this is going to lead us to these conclusions about confinement and chiral symmetry breaking. And I'm going to leave the description of this really nice story to Thomas's talk later in the day. Okay, so this leads me to part 2. Which is now let's do our controlled study for small supersymmetry breaking and understand what the predicted phase is in this soft supersymmetry breaking regime. And as I emphasized, the Kähler potential of the n equals to 2 theory plays a really starring role. It's exactly the thing that the supersymmetry breaking potential is mapped onto. So I'm going to begin with describing how we compute this Kähler potential. And before that, I just need to give a little bit of a necessary background on the n equals to 2 supersymmetric moduli space. So n equals to 2 super Yang-Mills in 4 dimensions has a moduli space of supersymmetric vacua known as the Coulomb branch. And this moduli space is parameterized by n-1 complex coordinates, which can be written in a gauge invariant way, at least at weak coupling, as traces of products of the vector multiplet scalars. So these are the standard basis for the Coulomb branch coordinates. And at a generic point on the moduli space, vevs for these coordinates, for these moduli, will break the SUN gauge symmetry to its Cartan U1 to the n-1 subgroup, and then the low energy description of the theory is going to be in terms of n-1 abelian vector multiplets. Now, importantly, there are singularities on the moduli space where typically BPS particles in the theory become massless. And So for example, famously in the case of SU2, Seiberg and Witten described how there are two singularities at strong coupling. So here is a depiction of the U-plane, the complex U-plane for the SU2 theory. I have one Coulomb branch coordinate, and I have two singularities at strong coupling. One is known as the monopole point and one the dion point. At the monopole point, a BPS state with magnetic charge 1 relative to this U1 gauge group factor becomes massless, which is why it's known as the monopole point. At the dion point, similarly, a state with dionic charges becomes massless. Now, the generalization of this picture from SU2 to SUN is, of course, very complicated. I have, for SUN, many more types of singularities, and the structure of these singularities is much more complicated. And today, the ones that we really need to focus on, or the ones that will play a starring role, are the n so-called maximal degeneration points in the moduli space. So these are the endpoints where a maximal number of n-1 mutually local dions become massless simultaneously. So these are the points that were studied by by Douglas and Schenker back in the 90s, and they are the natural generalization of the monopole and dion points to SUN. So there are n such points. They're related by some Zn symmetry that acts on the moduli space. And at one of these points, I'll call it the so-called multi-monopole point, the n-1 particles that are becoming light are monopoles in the sense that they each have magnetic charge 1 relative to one of the U1 gauge group factors. So really the direct analog of the SU2 monopole point. And then the other points are related by the symmetry on the moduli space. And at these other points, the states becoming light are dions. So this is a statement of just the supersymmetric theory. So in the supersymmetric theory, I have singularities on the moduli space. And so I'm describing here how like these singularities, in the SU2 theory can be generalized to singular points on the moduli space of the SUN theory. And yeah, so I haven't, so far we've taken a step, this is all supersymmetric. Yeah, thanks. Other questions? Okay, so with that context, let's study the Kähler potential in the n=2 theory, which remember this is our supersymmetry breaking potential. We're interested in the properties and especially minima of this potential. So let's start with SU2. So SU2, we can gain some intuition. The Kähler potential is just a function of my one Coulomb branch coordinate. And it's a known function. I didn't write it here, but it's some Gauss hypergeometric function. And I've plotted it here in the complex U plane. And in particular, it is convex. And it has a single minimum at the origin of moduli space where U equals 0. And at this minimum at the origin, the Kähler potential is negative. So also on this plot, I've plotted the monopole and dion points on the moduli space. They lie in particular on this contour, which is the contour where the Kähler potential is 0, which for SU2 it's exactly the same contour as the wall of marginal stability that separates the strong coupling region at the middle of the moduli space from in this case the weak coupling region. And so our single minimum at the origin of moduli space, which is the point about which you'd want to expand in our supersymmetry breaking analysis, lies in this strong coupling region within the wall of marginal stability at negative Kähler potential. Okay, and I mean this plot. I mean this was made long ago, I should say. Now, as I emphasized, we really care about generalizing this picture to SUN. And in SUN, my Kähler potential is going to be a function of now n-1 complex coordinates. And of course, it's much more complicated. So explicit integrate. So for our purposes with the supersymmetry breaking of this potential, we really needed the explicit like integrated solutions of the Seiberg-Witten periods in order to like understand like the shape of this potential. And explicit integrated solutions had previously been known for SU2 and SU3. In SU2, the Seiberg-Witten periods are, like I said, basically Gauss hypergeometric functions. I didn't write the exact formula here, but that's what they look like. For SU3, these are Appel F4 functions, and but we really care about SUN. And so, motivated by this supersymmetry breaking story, we were able to obtain last year a result for the Kähler potential for the general SUN n equals to 2 theory, which is an all-order Taylor series expansion for the Seiberg-Witten periods. There are n-1 pairs of them around this strong coupling point in moduli space, around the strong coupling region of moduli space where the origin of the moduli space. And so this expansion, I didn't want to write it explicitly on the slide. I mean, it just looks, it's a little long, but really like each monomial of my Coulomb branch coordinates can be given explicitly. The coefficient can be given explicitly as some simple function, which is like, depends on like gamma functions and trigonometric functions. And it's really nice and simple. So with this result, on the previous slide, and also with various other analytic and numerical evidences, we undertook this study of the SUN Kähler potential. And the punchline is that the SU2 picture, the points of the SU2 picture that I described remain qualitatively correct. So here, I've explicitly made some plots numerically of the SU3 Kähler potential in different slices. But of course, like we were looking at more general N. So, but here you can get an idea. So for the SU3 Kähler potential, here I'm plotting the Kähler potential in the complex U plane. So here there are two Coulomb branch coordinates, call them U and V. And so, for example, you can make a plot at fixed V in the U plane. And so this is a nice plot because, so here the origin of this plot is the origin of moduli space. And on this plot, you can see the three, in this case for SU3, three multi-monopole points on this curve. And so again, we find a minimum at the origin of moduli space. You can compute its value exactly. It scales at large n is minus n squared. So it occurs at a region of negative k at the origin. And then the region right around the origin is also at negative k. And then here I've plotted the k equals 0 contour in this plane on which the multi-monopole points will always lie on this k equals 0 contour. And so you can kind of think as this k equals 0 contour as some proxy for part of the boundary of this strong coupling region in the moduli space. And so, for example, on this plot, I'm plotting this like k equals 0 surface that surrounds this this strong coupling regime in the complex U plane, but now as I dial part of the other coordinates, you can see it forms this like kind of egg shape. It's kind of the analog of the egg shape in the wall of marginal stability in the SU2 Coulomb in the SU2 plot. Okay, so so we understand. I don't think so, but yeah, let's chat later. Thanks. Yeah, let's chat later. Thanks. Okay, so I told you that this is what the Kähler potential looks like. This is our supersymmetry breaking potential, which is really reliable in the soft supersymmetry breaking regime. And so we have this minimum at the origin of moduli space, and we should study its physics. So you can do so, and the answer is that this potential at this point is only going to give a mass to the scalars in my problem. So in particular, I'm going to have order n, or n minus 1, massless gauge fields and massless fermions. This vacuum at the origin of moduli space is going to be in the Coulomb phase. And the entire SU2 times Z4n chiral symmetry is going to be unbroken. So this is kind of an exotic kind of vacuum. And so I want to emphasize that this analysis is reliable in this soft supersymmetry regime with small supersymmetry breaking. But this would be a very, very surprising prediction for the IR phase of adjoint QCD. In particular, it's extremely far away from this, like phase with confinement and chiral symmetry breaking in the CP1s that I described earlier that one might predict. And so one of the takeaways at this point is that if adjoint QCD does confine and break chiral symmetry, then the true vacuum is going to require at least one phase transition away from this small m vacuum. So indeed, yeah, the one form symmetry is spontaneous. Okay, so I think I'm probably out of time. Exactly. Okay, well, I'll summarize. We're about done. So I told you that we can analyze our normalization group flow from n equals to 2 super Yang mills in the UV to adjoint QCD at low energies. So we want to use this flow to our advantage to explore the phase structure of adjoint QCD. Importantly, the supersymmetry breaking deformation that we're considering can be mapped to the IR of the n equals to 2 theory using supersymmetry. So this is a really important handle on this analysis. And so then we can start with our principled analysis of the soft supersymmetry breaking problem and thereby deduce the small m phase of this softly broken theory. And it's this kind of strange Coulomb phase with lots of massless fermions and photons and no chiral symmetry break. And this analysis really depended crucially on the data of the supersymmetric theory. I was here especially emphasizing the role of the Kähler potential, which we computed or which we analyzed. And so now the challenge is how are we going to describe supersymmetry breaking for larger values of m and ultimately make contact with adjoint QCD. And so this is going to be discussed in some detail by Thomas in the next part of this talk. So yeah, I'll end. Thank you. Indeed, that's how you should, and that's how one would interpret that. Yeah. This isn't a CFT. This is some free, with free like massless fermions and yeah. Well, oh, okay. The trivial CFT. Yes. Yeah. Well, so what I said is that I'm going to learn something about the supersymmetric theory motivated by the supersymmetry analysis. And so my example here is this Kähler potential. We did a whole, so we had to do this whole complicated calculation, which hadn't been done before in order to study its properties. And now that we have that, you can also use it to, this is a purely supersymmetric computation we had to do, and you can use it to try to learn things about the supersymmetric theory like itself, like about this like strong boundaries of this strong coupling region and so on. So here, the Kähler potential that we match onto is indeed globally well defined. And so in doing this matching, you can exactly like fix these like as improvement terms. These. Good. You're minimizing the thing which matches onto this onto this operator, and it's the Kähler potential up to like basically improvement terms of the stress tensor, and you can fix what those are. So this is fixed in the matching. Yeah. Yeah. So it will require a phase transition. Yes.
I also have a question. So if I understand correctly, it's long been known that the n=2 theory itself is not defined, right? So just make sure I understand. The surprise here is that you add a tiny mass for the scalar. It doesn't do what you would naively guess something defined that remains.
Indeed. So like this sort of like soft supersymmetry, it's kind of like a proxy for the Coulomb branch. It's like very similar to like the IR phase of the n=2 theory, right? So it's kind of like saying when I've added this small, like when this mass is small, I'm kind of getting a proxy for like the phase of the n=2 theory. Yeah.
And like spiritually, there's a huge literature on people starting with 2D theories, putting in a small 2D breaking, and then declaring that whatever the word can break up this extrapolate to the point without any phase transition, like anything paper that's doing this kind of thing.
Yes.
Not yours.
Yes.
But you're basically exposing that probably not.
Yeah, so our argument will not be that one should naively just extrapolate M in this. Yeah, we'll have some argument that. Yeah, so I have like these n-1 like photons. Yeah. Yes, exactly. Yes, yes. Yeah.
What happened for diagonal
Yeah. Yeah, so the reason we're looking at this one in particular is because it has these nice like this nice property of the tracking. So if you can make some argument that like supersymmetry will constrain your deformation, then you can look at other deformations. And then once you have, and of course once I have such a a proposal for a phase, I can deform away from adjoint QCD itself, like I described there's a deformation to, of course, delete one of the fermions, and I get back the n=1 theory. So indeed, you can consider like connections between these. Yeah. Well, yeah, it's in the same. Yeah. So in this case, this is the natural. Yeah. So I could, of course, always just add some like gaugino mass, and then I need some argument as to like why I can do anything in a controlled way. Yeah.
So I think I'm going to get for all the way. Yeah.